Okay, well, good afternoon, everybody. I actually wanted to start with a little bit of a testimonial about how interdisciplinary research happens and how ICTES can catalyze that. So I actually came to Virginia Tech in 2008. I'm in civil and environmental engineering, and many of you probably know that I'm very passionate about microbes and microbial ecology, and it's a really hot area with microbiome research. And it wasn't too long after I came here that Mike Coachella paid me a visit, and he was getting the VT Sun Center started, so the ICTES VT Sun Sustainable Nanotechnology, and we were talking, and he said, you know, we really need a microbial ecologist. And I said, wow, yeah, I couldn't agree with you more. But I don't know anything about nanotechnology. So I think this was a situation where, you know, here I am, someone new to the field, but then getting to know this network and collaborating with people, all sorts of neat ideas have been sparked. And so as I got involved with the ICTES VT Sun, I got talking with Lindsay and Pete about ideas. And so this was one of the first grant proposals that was funded just through talking to each other and being brought together by ICTES. And then later on, I got to know Scott Renneker, Maren Roman, and Sean McGinnis, who just spoke, and thinking about a very specialized engineered nanomaterial that's nanocellulose. And I think, you know, Virginia Tech is the place to be for nanotechnology, but especially nanocellulose is a very special kind of engineered nanomaterial. And we've got the opportunity to start doing research on that as well. So I will talk about both projects. And they both go along this theme of engineered nanomaterials. They're great, but what happens to them at the end of their life cycle when they're disposed of? What kinds of concerns might there be? And so we see them in all sorts of products, personal care products, cosmetics, pharmaceuticals, all these kinds of lovely things you see here. And so it is an important question to ask about their safety and what the impacts might be in the environment. I think especially, you know, you want to be ahead of the curve on this kind of thing and not just find out later that, oh, there's unintended consequences of this wonderful nanomaterial. And so there have been some studies emerging in the literature saying, yes, there is potential environmental concern for release of engineered nanoparticles into the environment, potentially accumulating in the food chain. And, you know, this, I think, relates somewhat to what Sean presented, you know, thinking big picture of production and use, and in our case especially, we're looking at this end of life. And with the EPA grant, Lindsay's been focusing on, well, what happens when you incinerate nano waste, right? And then we've been looking at then, well, what happens when they go down the drain and go to a wastewater treatment plant? One of the tricks with engineered nanomaterials in the environment is it's really hard to monitor for them. I've worked a lot on organic pollutants and metallic pollutants, but with the nanomaterials, you know, it's not enough to just say it's there. You need to show that it's in nano form. And so there's only a handful of literature that's actually tried to monitor these in the environment. But of what's out there, it does seem apparent that wastewater treatment plants are an important route of disposal and where they accumulate and then can impact the environment. So for those of you who don't think about wastewater treatment plants every day like I do, this is what they're all about. So you have various treatment processes going on. Me as a microbiologist, I'm very interested in this biological treatment step. Then you have separation of those microbes, some sort of disinfection, and then it just goes out into the environment and gets used again. The sludge is also important because it's often land applied as a fertilizer. It can be incinerated. That puts it back into Lindsay's ball court to look at. Okay, so the microbiology of waste treatment. It is a very fascinating, in my opinion, intricate, complex microbial ecology that we have to thank for treating our waste. And really central to this are these organisms that perform nitrification, so they get rid of ammonia waste. Well, it just so happens that these are also very sensitive, slow-growing, kind of picky organisms, and so we kind of have to baby them a little bit to get them to do their work in a wastewater treatment plant. And there are studies in the literature with pure cultures of these guys showing that, yes, when they're bombarded with nanoparticles, they're not very happy and don't perform very well, and that could be a problem. But we're interested in, well, what about real communities, not just a pure culture, but a mixture that's in a real sewage treatment plant. And what are some things that could happen to engineered nanomaterials? They could persist, aggregate, react, and then in terms of microbes, there's times when they're taken up in the cell or they absorb to the surface of the cell, and that can interfere with function, or they might be converted into something else that's either better or worse for the environment. Looking a little bit deeper, so there might be damage to the DNA. There could be, if you have things aggregating at the surface, interrupting the function of the membrane, which is really critical to microbial function. If you're combining it with disinfection, right? So we disinfect wastewater effluent with UV or chlorine. You might be getting reactive oxygen species, which might be detrimental. And so these are various levels that we've looked at. Microbial community as a whole, the nitrifying bacteria, which are very important for function and maybe like a canary in a coal mine. Many of you know I'm passionate about antibiotic resistance, and this has kind of been a nice synergy there. We know that we flush antibiotics down the drain. They're in wastewater treatment plants. We know wastewater treatment plants are a hot spot for resistant bacteria. What about nanoparticles, especially ones that are metallic, ones that might stimulate resistance to antibiotics? Because metal resistance and antibiotic resistance are very similar in their functions. And then just overall toxicity is something that we're concerned about. So for those of you who have had the pleasure of paying us a visit to the lab in ICTEST 2, we have these mini wastewater treatment plants set up in duplicate, and that's our test bed where we feed them different kinds of nanoparticles, and we see what happens to the microbial community. We've been working with VBI to use next generation DNA sequencing to get really precise measurements of what happens to the microbial community. And so far we've tested nano silver, nano iron, TiO2, and nano cerium oxide, which connects nicely with what Lindsay just presented. Okay, so these are some of our initial results we've seen with next generation DNA sequencing. So we can look at these mini wastewater treatment plants at the beginning and end of operation. So E means end, B means beginning. We've got control, ones that got nanomaterials, and then ones that got like a surrogate, the non-nano form. Now, microbial communities in themselves are something that evolve and change with time. So it's just that part alone is interesting, how these change, but then we can see how the nanomaterials may or may not affect that. And just to give you a little appreciation here, each one of these lovely points is actually 3,000 DNA sequences. So with next generation DNA sequencing, the beauty of it is that you get all this data, but then the problem of it is that you get all this data and you got to boil it down into something that you people can all look at and sort of make sense of. And so basically, if there's a circle around it, it's statistically similar. So we did see that the ones fed ionic silver migrated differently. But the nano silver were similar to the controls. So that might be good news that maybe nano silver was less toxic than the ionic silver. That's believable because maybe it's less bioavailable. And then we did the same thing with the titanium dioxide. And here's where just the communities as a whole migrated from beginning to end, but in a similar way, and there really was an effect of nanomaterials. So again, potentially good news. And we're now working on some of the other nanomaterials to see if it tells the same story. Now, one thing we've seen in the data, just looking at the performance of these systems, we've been starting with really low doses. so-called environmentally relevant doses, like 0.1 milligram per liter, and then ramping up and looking at changes in functional genes and groups. It looks like it's right towards the end when we've ramped up the dose that maybe we're getting an effect. So we're going to repeat these experiments and start with that higher dose. And I think that's relevant as well because you have accumulation, and studies so far say that they accumulate in the sludge.